All right, what we're going to be talking about is section 12.3, which is talking about measures of dispersion. And dispersion is just basically talking about how spread out is the data. And when you're comparing sets of data, the data that's spread out more is not necessarily as accurate a representation as the data that has a smaller spread. So we're going to be talking about some of the methods are range. We can calculate the range of the data. We can talk about the standard deviation of the data. We can figure out how to interpret this measure that we get, and something called a coefficient of variation. So again, we just said dispersion is just talking about the spread of the data. How far spread out is the data? And again, the bigger the range or the bigger the spread, when you compare more than one set of data, that can represent more accuracy or less accuracy, depending on what the comparison is. So the first one is just called the range. And to figure out the range of a set of data, all you have to do is just take the larger value in the data set and subtract it from the smallest value in the data set. So sometimes when you're calculating range, you have to be careful that there could be a large set of data, and you want to make sure that you are accurately taking the largest and the smallest value when you do that calculation. So if I have this set of data, and both sets of data have the same mean, in other words, if I take the 1 plus 2 plus 7 plus 12 plus 13 and divide it by 5, I get the mean, and they have the same median. Okay, and once again, we'll figure this out one day, why it does this. Okay, again, they both have the same mean and the same median. So what we're going to be looking at now is what is their range. So if we look at the first number to figure out the range, we're going to take the highest number, which is 13, and subtract it from the lowest number, which is 1. So the range of this data is 12. On this one, take the 9 and minus 5, so the range of data is 4. So considering that they both have the same mean and the same median, since the first set, A, has a range that is 3 times as big as B, then we would probably say that B is a more accurate representation of data. Again, that doesn't necessarily mean that there's anything wrong with set A. It just means that set B might be a little bit more accurate in terms of the mean and the median. Okay, so one other form of dispersion measurement is what we call a standard deviation. And so the process of finding the standard deviation is a little bit time consuming, but it is a very, very common calculation that is used very, very often to evaluate data and determine what kind of information we have. So I'm going to step you through this a little bit at a time. So what we want to do first is find the average of this set of data. So the average of all these numbers is 7. Okay, and then what we want to do is take each data value in the list and subtract it from the mean. So in order to calculate this number here, we did 1 minus 7. And here we did 2 minus 7. And here we did 8 minus 7. And here we did 11 minus 7. And here we did 13 minus 7. Now, we want the negative numbers, because what we have to realize is that if we add all of the deviations together for any set of numbers, it will always be 0. So that presents our problem. We can't just find the average of these deviations, because if I just take those numbers, -6, -5, 1, 4, and 6, and add them together, I always get 0. So it would tell me that the average is always 0, and that's not an accurate representation. So what we do is we take these numbers and we're going to figure out something called a variance. we're going to take all of those numbers that we got and we're going to square them, because when you square a negative number, you end up with a positive. So we're going to take all of these numbers and square them and get 36, 25, 1, 16, and 36. And we're going to add those numbers together and figure out the average. And so when we add those numbers together, we don't get 0 this time, and we have a little bit better representation of what the spread is. So we're going to add them all together, and we're going to divide by n minus 1. And at this point in time, you'll accept the fact that we're doing this. It is not a population, it is a sample of data. So again, whenever we're talking about a sample of data and we're finding standard deviation, we always divide by n minus 1. If it were a population, then we would divide by n, and we do get a different representation. So standard deviation is denoted with the small lowercase letter s, and that's the sample standard deviation. If I was doing population standard deviation, then I would have the lowercase sigma symbol as my denotion. So the reason this is important to keep in mind, if you're using some sort of calculator, like a graphing calculator, and you're calculating the standard deviation of this population, then the representation that you're going to see on your calculator is either going to be an S or the sigma symbol. So you've got to know which symbol to look at. Now, on the test and everything, I do not have graphing calculators listed as an option. So you need to make sure you're comfortable doing this without a graphing calculator. So when we're looking at this formula, the variance is this part of the problem underneath the radical, underneath the square root. So this is what we refer to as the variance. So what we have to do is calculate the variance and then take the square root of the variance, and that is the standard deviation of the sample. So let me explain to you what this is saying again. X bar is your average. So it's saying take each number in the data set and subtract it from the average. So if we go back again, a couple slides, we took each data value, 1, 2, 8, 11, and 13, and we subtracted it from 7, and we got 1 minus 7 is negative 6, 2 minus 7 is negative 5, 8 minus 7, oh, how did I get that? 8 minus 7, that should be a 7 instead of 1. 8 minus 7 is 1. 11 minus 7 is 4, and 13 minus 7 is 6. And then we're going to take each of those numbers, we follow order of operations, and we're going to square those numbers. And then we're going to summation, meaning we're going to add them all up. And then we're going to divide by n minus 1, because again, we're talking about a sample standard deviation, not a population. So here's our steps, and then we're going to do an example. Calculate the average of the numbers. That's step 1. You can't do anything until you've got the average. Find the deviation from the mean. In other words, take each number in the list and subtract it from the average. Take those numbers and square them. Not square root, but square them. And then we're going to add all those numbers together and divide by n minus 1, and then we take the square root of that answer. So let's look at this. So we have the numbers 1, 2, 8, 11, and 13. So if I find the average of those numbers, the average is 7. So X bar is 7. And again, I did that by taking the 1 plus 2 plus 8 plus 11 plus 13 and dividing it by 5. So then let's look at a chart, because it does help to put this in some sort of chart format. So I take each number in my data set and I subtract it from 7, or subtract 7 from it. And that's where I got the negative 6, the negative 5, the 1, the 4, and the 6. Then I take those numbers, negative 6, negative 5, 1, 4, and 6, and I square them, and I get 36, 25, 1, 16, and 36. I add all those numbers together and I get 114. So this 114 represents the summation of x minus x bar squared. So it represents the numerator of our calculation. So then I'm going to take the 114 and I'm going to, remember again, our formula is summation of x minus x bar squared divided by n minus 1, that's our variance, and the square root of all of that. So we're taking that 114, which was this number on top from the last screen, we're dividing it by n minus 1, so we're dividing it by 6 minus 1, which is 5, and we get 22.8. Take the square root of all of that, and we get 4.77. So this is my standard deviation. All right, let's look at another example. I have the numbers 2, 5, 6, 8, 9, 11, and 15. So let's go with a chart because it makes it so much easier. Again, so here are all my numbers. If I take all of these numbers and I find the average of those numbers, I take 2 plus 5 plus 6 plus 8 plus 9 plus 11 plus 15. The average is 8. So I end up with the numbers 2, 5, 6, 8, 9, 11, 15. The 6, or the negative 6 here, is 2 minus 8. This number is 5 minus 8. 6 minus 8. Oops, that should be negative 2, sorry. 0 minus 8, sorry, 8 minus 8, sorry, 9 minus 8, 11 minus 8, and 15 minus 8. I'm having a hard time writing. 15 minus 8. So then I take each of these numbers that I get and I square them. So I get 36, 9, 4, 0, 1, 9, and 49. And I add all those numbers together and I get 108. Then I take the 108 and I divide it by 7 minus 1 because n is 7 in this situation. I get 108 divided by 8, sorry, 108 divided by 6, which is 18. The square root of that is 4.24, so this is my standard deviation. So how do I interpret this information? So what we have to do a lot of times is compare data when we're doing this to make sure that what we're seeing is accurate. So let's look at this example. And I have two companies that sell sugar packs for coffee. Company A, the average pack when it was explored had 1.013 teaspoons of sugar in it. And for company B, the average pack had 1.007 teaspoons. So when you're comparing those two pieces of information, you look at that and you would probably say that company B is more accurate of 1 teaspoon of sugar than company A. Assuming that you only want 1 teaspoon of sugar in the packet, company B is doing a better job. So then when you look at the standard deviation of the information, you'll notice that the standard deviation for B is 0.0018 and for A is 0.0021. So when you're comparing this information and you want to know which company is more consistent about it, what you would end up saying is that company A provides more sugar than company B. They have a larger mean. But that's not necessarily a good thing. If you're trying to get a 1 teaspoon packet, then company B was doing a better job. And then we're going to say that company B, excuse me, is more consistent about this than company A because they have the smaller deviation. So that means that company B, according to using the standard deviation, is doing a better job of packaging their sugar than company A. You were able to look at that and possibly derive that from the mean, but given what if the means were closer together, you might not have that information. So another piece of data that's going to help us, especially as we get further along, is something called Chebyshev's theorem. And with this, we are able to figure out approximately how many pieces of data are within a range or within a standard deviation. So let's say that K is 2 standard deviations from the mean. Then that means if I do my formula, 1 minus 1 over 2 squared, because I'm looking at 2 standard deviations, would be 1 minus 1/4, which is 0.75, or 75%. So what that tells me that at least 75% of the data will fall within 2 standard deviations of a curve. Now this is assuming, this is sort of important, this is assuming that it is not a normal curve or not symmetric. If it's symmetric, we're going to learn in section 4, that there's something called a normal curve, and there's even a more accurate representation. But Chebyshev, what he figured out was that in almost all sets of data, no matter what the curve dimensions are, once you knew what that average was, that 75% was at least 2 standard deviations away, and you could figure out for each of the standard deviations. So let's look at the next one. The next example says, how many lie within 3 standard deviations of the mean? And so if we do our formula, 1 minus 1 over 3 squared equals 1 minus 1/9. And 1 minus 1/9 comes out to be 0.888 repeating, which is approximately 88.9% of the data. So again, 88.9% of the data is going to fall within 3 standard deviations of the mean. And again, the one thing that I do want to stress with this is that this is not for normal curves. This is for any curve that I could give you. When we start talking about normal curves in the next section, those numbers will change slightly. All right, so the last thing we're going to talk about is something called a coefficient of variation. And a coefficient of variation is not just a measure of dispersion, but it's also looking at the average and the percentage, and it's basically an average of those two numbers. So to find the coefficient of variation, we're going to take S, and remember S is the standard deviation, and we're going to divide the standard deviation by x bar, which is the mean. So remember, this is talking about a sample. If we're dealing with a population, we're using the same values, but we're doing the sigma, which is the standard deviation of the population, and we're doing mu, which is the average of the population. So here we want to compare the dispersions of these two samples for A and B. So using your calculator, you can do all of these calculations that you need to do. So what I've done is I've gone ahead and calculated them. So what we have here is in sample A, the average, which means 12 plus 13 plus 16 plus 18 plus 18 plus 20 divided by 6 is 16.16. The standard deviation, which is a lot more calculations, but we just went through examples with that, the standard deviation of sample A is 3.125. We do the same calculations for B. I take the 125 plus 131 plus 144, 158, 168, 193 divided by 6, and the average is 153.16. The standard deviation is 25.294. So when I want to figure out the coefficient of variation, I'm going to take the 3.125 and divide it by 16.167. And when I do that, I get 0.193, and then I want to multiply by 100, so I get a percentage, and I get 19.3. Oops, 19.3. And then over on sample B, we're going to do 25.294 divided by 153.16, 0.167, and I end up with 0.165. Again, multiply by 100, and I get 16.5. So it shows you that sample B has a larger dispersion than sample A, but sample A has the larger coefficient than sample B. So again, if we look at the standard deviation of B is bigger than the standard deviation of A, but the coefficient of variation for A is bigger than the coefficient for B. So this gives us more information that we can compare, and as we go through the rest of chapter 12, we'll learn how to use this information and compare the information. Make sure you're keeping your notes really accurate. You can use these notes on your test, so you need to just make sure that you have information in front of you that you can look at as a reference. Keep in touch with me and let me know if you're having any problems, and have a great week.